Okay, so thank you very much. I'm going to be talking about topological advection, and I will certainly explain a lot about what that means as a general problem. This is work that I've done with some undergraduate students of mine, Sierra Dunn and Wynn, and also some of my collaborators at the University of California, Merced, in particular, Kevin Mitchell. So what is topological advection? First of all, I'm going to talk about two different advection problems in general, and then we can see how the topology comes into this. So first of all, a nice classic advection problem is to ask the question of how can we quantify mixing in a given situation? And by the way, all of what I'm going to be talking about today is in 2 dimensions, and later we'll see how this might be ported up to 3 dimensions. So thinking about mixing in 2 dimensions of a fluid, and in particular passive scalars that are being advected. There are many different measures, but one that we're going to think about in particular is something called topological entropy. Now, this measure essentially gets at the amount of stretching and folding that occurs within material lines, but in sort of a more dynamical systems perspective, if you're able to describe a flow map of the field, and then look at the exponential growth rate of distinguishable orbits, periodic orbits of this map, then that growth rate, that exponential growth rate is the topological entropy. But that's a pretty hard measure to actually be able to calculate. So what we are going to think about, is the growth rate of material lines. So if you look in the bottom left, you can see this line that is being advected. This is with a zonal jet model, the Bickley jet. And it's just getting stretched out exponentially over time. And if you look at that, it'll be exponential stretching, and this topological entropy can be put as a lower bound to it can be the exponential rate that it's stretching at. Now, this is something you can use all over the place. You can look at looking at the mixing of passive scalars in the ocean for oil spills, or even just other passive scalars like temperature or oxygenation. One of my favorite examples is in the upper left. This is actually a little piece of art from fluid marbling, or paper marbling, where you just put paint on the surface of a fluid and you stir it around, and then you put a piece of paper on, and then you pull it off and you get a nice image like that. And in particular, we're going to see how we can get topological entropy in a very nice manner. Okay, another second problem that you can pose for topological, or for advection, is the idea of trying to detect coherent structures. So I've shown this Agulhas ring, which are these large vortices that are shed off the southern coast of South Africa. And these large vortices entrain passive scalars like oxygen levels, or here you can see there's phytoplankton that are entrained in this vortex. And if you want to be able to detect these, there are a number of different ways, but we want to think about how to detect these in a very general sense. One thing that you can do to define them is that these have a barrier that acts as, well, a barrier to transport, and we can define them as regions that do not mix substantially with fluid outside. So we can think of it in the following sense. If you have a defined barrier to transport and you advect it forward in time, it does not appreciably stretch out. So it's sort of like a dual problem to the previous mixing one, in the sense that you're looking at looking for loops that do not stretch out very much, whereas previously we're looking for ones that do stretch quite a bit. And just to show you, there's another view of the Bickley jet, and you can see these vortices that are rotating around. Okay, so these two problems have the same sort of presentation. For both of them, we have some material line or curve that we want to see how it's advected forward. So it's a very general problem. And we're going to look at this in a particular regime. Normally, you might look at this in what we might think of as the full set of data regime, where you have a flow map or a velocity vector field, or you have some sort of total information like that. And a lot of work's been done in that, and I think it's not as interesting, to my mind at least, as what you can do when you have sparse data. And this is actually the case where it sort of corresponds to experiment the most. And sparse data, I just mean you have a number of advected trajectories, and you know their positions over time. So we're going to deal with this. Now, where does topology come in? Well, it comes in sort of two different ways. The first way is how we're defining curves. So we're going to define material curves up to homotopy. So what we can loosely think of that as is if you look at this loop right here, we're going to look at the equivalence classes of that loop. So we're going to look at all the loops that are the same as that, sort of deforming it without actually pulling it over any of these distinguished points. So classifying these up to homotopy. The second place where topology comes in is really in how the points move about each other. So a good example of this is in thinking of stirring protocols. So down here I have these 3 points, the red, green, and blue. And the first stirring protocol we can think of is, say, take these 3 points, imagine them as maybe rods that are in a fluid, and they're going to execute pairwise interchanges. And this first protocol, you can take these left 2 or right 2 points and switch them in a counterclockwise direction, and then switch the left 2 points in a counterclockwise direction. And if you do that, you can see they move this material line around, but they don't stretch it out that much. Now, in contrast, if we just take this clockwise and switch it to counterclockwise for one of these 2, it makes a huge difference. So these points are moving about each other. They're still doing the same amount of movement. There's still the same amount of work being done on the fluid. There's still the same amount of kinetic energy, but there's a vast difference in the amount of stretching. So this tells us very much that it's how these particles loop about each other. It's the topology of how they move about each other that's the salient point for how much mixing occurs. So we're going to today think about topological algorithms that actually do this, take an initial curve and find out what its final condition is. And there are a few here, the Bestvina Handel algorithm, there's a braiding approach, there's one I've done with my collaborators that we call E-tec, and today I'm going to talk about another one that's actually sort of the most general of the bunch and much more efficient that we call dual E-tec. All right, so the first thing we want to think about the trajectories as braids. So we're thinking about them in 2 dimensions, and as time flows downwards, they trace out braided patterns. So you can see that in the upper left. And topologically speaking, we can take that geometric braid and turn it into a series of generators, algebraic generators. And this algorithm, the Bestvina Handel algorithm that's been around since '95, basically it takes a material curve, and it's represented in terms of something called a train track. We're not going to get into really what that means, but a loose description of it is here. If we have a curve that goes around these points, you take all the parts of the curve that are parallel to each other and flatten them, and you can get a graph that looks like this over here, where the weight of an edge of the graph corresponds to the number of sort of bands that are parallel to each other. So it's sort of a nice way to compactify this information. And the Bestvina Handel algorithm takes this train track and it moves it around under the action of the braid, and it finds a transition matrix for these elements of the train track. So it tells us how this curve maps back to itself, and therefore how much stretching occurs. So you can do a lot of interesting work with this. The problem is that this only captures the asymptotic behavior, and you have to have periodic trajectories, and we're thinking of the general case of the motion of points, say, that are advected in the ocean. And obviously that's not going to necessarily be periodic. It's also very computationally slow. So this is something that doesn't work for more than 20 trajectories or so. So sort of the next way that people have thought about this is so-called braiding approach. Again, you have a braid that is representing your trajectories. And you can take each point of the braid and sort of lay it along a line here. So this 1 through n here. And you have this disk, and there are these lines. These lines are going to be a way that we put a coordinate system on our loops. So if you have a loop like this up here, you just count up how this loop intersects these lines. And each of these lines, therefore, is sort of a coordinate on this loop. And overall, you can have a nice coordinate that can encode any possible loop you could ever want to put on this space. And what do you do? Well, if you interchange 2 particles, that has an action that acts on this coordinate system and updates it. And then if you do this over and over again, you can find the total length and how that stretches out over time, and you can define the finite time braiding exponent. That's something that Jean-Luc Pifot and others have defined. And you can solve this advection problem in a very nice way. And this is much more computationally efficient. And it has a lot of nice features. However, there is a number of drawbacks. First of all, you're taking this information that's inherently two dimensions, these points that are sprinkled over a two-dimensional domain, and you're projecting it into one dimension. You're projecting it away into one axis. And that gets rid of a lot of good geometric information. Secondly, the computational complexity of this is not as good as we can do. It scales with the number of particles squared. So very quickly, this can get bogged down with a large number of particles. So we're going to do better than this. We are going to introduce this new algorithm. I'm calling dual E-tec for right now. Might be a different name at some point. It's sort of just our working name. But it starts with a few ingredients. The first one is we likewise need to encode and have a coordinate system for loops. And what we do here is take the points, as you can see up here, and put a triangulation on here. This is in particular a Delaunay triangulation. It doesn't need to be, but this is a triangulation. And every time we have a loop, so that's this dotted line, is just a cartoon, you have every edge that it passes through, you give it a weight of 1. So the edges, once again, encode the number of times the number of transverse intersections of this material curve. And in that way, the entire triangulation can encode any loop that you possibly could want. And it encodes the sort of the topological equivalence classes of those loops. Now, we also need a way to evolve this forward. So if you look, I have this triangulation, it's evolving forward. And all that it's doing as the points move, you update the triangulation in one of two ways. You can either say, we're going to update it every time we have a triangle collapse. Then you're going to take this horizontal line and switch it to the vertical. So it's just a flip of a particular line. You can also update it and keep a Delaunay triangulation. There are a number of ways, but the main point is that there are these discrete topological events, and each time it occurs, you're updating the triangulation and therefore updating the coordinate system for this loop. And the final thing is you need to know how this updating of the triangulation acts on your coordinate system for the loop. And it's actually very, very simple. If you just have these two triangles and you flip this diagonal line, or the line that connects them, and that's what we saw these topological events are, then there's a very simple rule that gives you the new weight of this new edge. Unfortunately, it's not linear. It's very close. It's a max plus algebra, but it means that this is a slight bit more complicated than a large linear algebra problem. Still, it's conceptually fairly simple, the update rules. And here's just a little example. If we have these two triangles, you can see bands going through them. And if we switch this diagonal, then you can update and find the new diagonal edge. So fairly simple. So let's see how this works. So here I have a quadruple gyre, and these black lines are representing a curve that's being advected around. And over time, the weight of this curve is increasing. And here's a graph over here on the right of the log of the weights over time. And you can see it very quickly becomes a nice straight line. So therefore, it's an exponential, and the rate at which it increases is the topological entropy of this flow. So you can pull out the topological entropy very nicely. The other problem, confirming that you've found coherent structures. So here I've shown a little loop, and as it evolves forward, you can watch it. It will have periodic boundary conditions. It'll loop back, and it's a curve that over time does not appreciably grow. So it doesn't have exponential stretching, and therefore is a good candidate for a coherent set. So we can do both of these things fairly easily. Now, in terms of the algorithm and comparing it, up on the left over here is a log-log plot of two things. We're looking at the runtime of the algorithm on the vertical axis and the number of points. So as you add more points, it takes longer to run these algorithms, obviously. And the Braid lab, so the software or the algorithm that's based on the braiding approach, That is an algorithm that goes as n squared. So you can see that in this red line here. Our approach is roughly proportional to n. It turns out it depends a little bit on the nature of the flow. If you have just purely vertical flow, then there are going to be very few of these collapse events, and it is going to be something that scales much nicer. On the right over here, I have basically the same plot, but it's comparing sort of our old algorithm, E-tec, to the new one. And they both scale the same way, but there's a big difference in the amount of time that it takes overall. So it computationally is much more efficient, and that allows us to access all these different types of problems that are previously inaccessible. You can do tens of thousands, hundreds of thousands of particles in a reasonable amount of time. Some nice features. This, like I said, is much faster than the braiding approach, also faster than E-tec. It preserves the 2D geometry, so you can exactly see how these loops evolve forward in time. There are a few other things, but most of all, it's a fairly conceptually simple algorithm compared to other things out there. And one final note that I would say is that, in a sense, this is the natural way to think about things, in the sense that this approach is more general than the braid approach. You can actually derive the braiding approach from this approach. So the Denikov coordinates over here, you can actually get the update rules by just using these flip moves over and over again. So it is sort of the most natural way to deal with problems like this. Okay, so sort of in conclusion, we have this. Well, first of all, I want to sort of present the idea of a class of problems, a class of advection problems that I'm calling topological advection, which is to say, what can we say about the advection of material curves in the presence of or within our knowledge is just of the sparse data trajectories? What can we say about the evolution of these? So I think that's a nice sort of encapsulation of a sort of a problem area. So we introduced a new approach that we're calling dual E-tec. It is the current fastest algorithm that you can use for this type of problem. And it has a lot of other benefits. Some of the things that we're doing with this, so we have started applying this to some interesting systems. There's a paper that we published last year in Nature Physics, applying this to active pneumatic systems. So this little picture up here on the upper right is an image of microtubules, a bunch of microtubules that when you put a bunch of ATP in, they slide across each other. And so sort of they create this emergent flow structure that you see up there. And it's a nice example of a system where at the small scale, it's dictated what the stretching rate is, and then the flow emerges from that, sort of the opposite of what we usually have, where you're having some global constraint of mixing, and at the small scale, stretching emerges. Anyways, we analyzed the system using this sort of topological method. We're working on extending this to 3 dimensions. Now, in 2 dimensions, the topological restrictions are perfect. In 3 dimensions, less so. So that's something that we are working on. We're also working on an extension to this that would be a little bit better suited to experimentalists. In experimental data, you have trajectories that pop into and out of existence in terms of when you actually detect them and when they go away. And so we have a natural extension of this algorithm to deal with that. And we're working on applications to be able to actually detect coherent structures. And there's sort of a wealth of different things that we're trying to apply this to. All right, so thank you very much, and I'd be happy to take any questions at this point.
Thank you very much, Spencer, for your nice talk, and which was quite rich in individual sense, at least to me. Thanks a lot. From the side of the audience, okay, I don't see many questions. Please, we have still time. If you have some questions, ask. Meanwhile, again, I can take advantage of the time. Okay, I have a very nice question. When I saw these trajectory motion as a braid, where you showed these nice simulation, nice figure. I thought of if it is, yeah, if you go back, right? Yeah, if I was wondering if very naively, if it can be possible to, yeah, exactly, to track these trajectory motions in this representation as a braid by using some Lie group geometries, because they really seem like, I mean, they follow specific vector fields.
Mm-hmm.
I mean, could we think them as integral curves of a specific Lie group? Because they show some sort of spiral-like structures, and it
Well, so I should
reminded
say
me
this,
Heisenberg group integral curves, and very
yeah,
naively, as I said.
so it all depends on where your data is coming from. So if you have some analytical system that is producing these trajectories, and your analytical system has the properties that could, you know, have these as integral curves, then sure. This right here, I should say, is just a non-physical simulation. It's just taking 3 points and then pairwise switching them in circles. So it's not actually coming from any sort of analytical model. It's just meant to be a 3D geometric representation of this braid right here. But I have actually, well, trying to think of what depth to answer this one in. I mean, braids in general form a group structure. So there is a rich group structure that you can avail yourself of. I mean, not Lie groups, it's a nice finite group. But there is sort of a group structure there. And there's a lot of work done on the theory of basically surface mappings. This is stuff that William Thurston did a lot of work on. But looking at the, I'd say, geodesics on surfaces that are preserved under mappings, and a lot of this stuff comes into play in that regime.